Welcome to the deep dive. Today we're plunging into, well, a really fascinating area, AI's next frontier. We're talking next generation reasoning models.
That's right.
We're going to unpack some insights from Nathan Lambert. He's a key voice at the Allen Institute for AI, AI2, and also Connects.ai. Our mission really is to cut through some of the noise, forget just the high benchmark scores for a minute. We want to look at where AI is really headed. How do we skate where the puck is going?
Yeah.
So we'll explore some surprising new applications popping up, maybe some hidden challenges in actually building this stuff, and what it really takes to train these incredibly powerful models.
And what's so interesting here, I think, is that shift in focus. It's moving beyond just hitting a higher score on a test.
Right.
This deep dive, hopefully, will show how this more sophisticated AI reasoning is already unlocking some genuinely powerful new applications. But maybe more importantly, it sheds light on the human effort needed. It's significant pushing these boundaries.
Okay, let's unpack that. So many of us get the basics of AI scaling, bigger models, more data. But what are some of these new language model applications, the ones coming out of this reasoning training?
Well, we're seeing models like O3. That's one from a major AI lab, and it's incredibly good at finding very specific, very niche information.
Okay, like what?
So, for instance, you could ask it for a download link for a specific research paper, say Coast Runners, and it just gives you the link directly.
Yeah.
No endless web searching.
Huh, that's unusual.
It is. It's an unusual but highly efficient use case.
Yeah.
And it signals, I think, a wave of new, interesting things coming down the pipe. Really practical stuff.
That is a powerful example. What about some other tools emerging? I've heard names like deep research and cloud code thrown around.
Absolutely. Deep research, it's remarkably steerable. You can get really creative with it. Like, you could prompt it to scan your website specifically, just looking for typos.
Oh, interesting.
Or tell it to only analyze content from your site. It gives you that kind of fine-grained control. Cloud code, on the other hand, it's got, people say very good vibes.
Good vibes.
Yeah, so maybe not for the serious, hardcore software engineers, but it lets you experiment playfully. Use your company's API keys maybe to help knock together a website without doing all the heavy lifting yourself.
So lowering the barrier to entry.
Exactly, making it easier to just try things out. So these are real uses people are already finding value in today.
Okay, so that's what's happening now. But what about the bigger picture, the more advanced stuff like fully autonomous agents or codecs? What are their current limits? What's next?
Yeah, the form factor, the basic idea for autonomous agents, it's clearly poised for success. Some people are already getting real value.
But there are limitations.
Oh, definitely. Right now, there's often a lack of, say, direct GPU integration for really complex machine learning tasks within the agent itself. And a lot of open models don't have built-in internet access, for pulling up Hugging Face configurations or things like that.
Practical hurdles.
Practical hurdles, exactly.
Yeah.
But the predicament is pretty firm.
Yeah.
These are likely to become day-to-day tools within maybe 6 months or so.
6 months. That's fast.
It is fast. And it's really thanks to this step change in performance we're seeing from the new reasoning models. That's the key enabler.
Now, here's where it gets really interesting for me. This progress, it isn't automatic, right? It's not a given. We hear about older models like, say, GPT-40 hitting a kind of saturation point for some things. And then newer models like O1 come along and push the frontier and time horizon for tasks way out. So what does all this mean for how AI actually gets developed?
That raises a really important point. These AI gains, they aren't free. They don't just happen. Sure, specific tasks will get faster, more accurate, no doubt. But pushing the limits, that isn't some predetermined path we're just cruising down. It takes significant, deliberate human effort.
Human effort.
Yeah, we need to think differently about training. We need to incorporate real planning capabilities, going beyond just basic reasoning skills. That's what's needed to make these early stage applications and products truly reliable, truly shine.
Okay, so planning is key. And Nathan Lambert, our source here, proposes a taxonomy, like a way to categorize the different traits needed for these models. Let's break that down. First up, skills. What does he mean by skills?
So skills, that largely covers what we've already gotten pretty good at. Models becoming highly proficient in things like math and code.
The basics on them.
The foundational stuff, yeah. And inference time scaling was a huge enabler there, getting faster at doing the calculations. But a more recent development, and this is crucial, is integrating tool use.
Tool use.
Yeah, you see this in models like DeepSeek and Qwen. It's why something like O3 feels so different. It's that combination of strong reasoning and the ability to use external tools effectively that really expands what they can actually do.
Right. Interact with the world, not just generate text.
Exactly.
Okay, next trait. Calibration. This sounds absolutely vital, especially if you're building real AI products. Why is calibration so important? What's the problem it solves?
Oh, it's critical.
Yeah.
Because these models, left to their own devices, they tend to just overthink like crazy.
Overthink.
Yeah, they generate way too many output tokens for the problem at hand. They need to learn how to adapt.
Yeah.
Use fewer tokens for simple problems, more for complex ones. Right now, it causes real friction for users.
How so?
Well, you often have to manually switch between different models, or maybe use those little reasoning and off selectors you see sometimes.
Oh.
Think about it. You ask a language model, what is 2 plus 3? Simple, right? It might spit out hundreds, even thousands of tokens trying to reason through it, when really a single token answer 5 is all you need.
Thousands. Wow.
Yeah, it can be 10 times, even 100 times more tokens than necessary. And that directly translates to much higher infrastructure costs, much higher latency. You could be waiting minutes for a simple answer. It's a huge drag.
Okay, so calibration is about efficiency, stopping that waste, making it less frustrating. That makes sense. And this connects to the next big piece, planning, which Lambert splits into strategy and abstraction. Let's start with strategy. What does that mean for an AI?
Strategy is, well, it's about the model knowing how to proceed logically, how to head in the right direction for solving a problem, and maybe what different approaches it could try.
And current models aren't great at this.
They really struggle, especially with changing course. If they start down the wrong path on a plan, it's very hard for them to back up and try something different.
Can you give an example?
Sure, imagine a model tackling a complex math problem. If it just dives straight in without any real planning, without sort of sketching out an approach first, it could easily output, say, 10, 20, even 40,000 tokens of just useless calculation, going completely the wrong way.
That sounds expensive.
It is. That's multiple dollars of compute cost right there, plus significant waiting time, all totally wasted. And in many applications, there are built-in timeouts. So if the agent goes astray or gets stuck, the user often just gives up. The whole interaction fails.
Right. So strategy is about picking the right path and being flexible. What about the other part of planning? Abstraction. That sounds quite deep, almost human.
It absolutely is. Abstraction is the model's ability to look at a really hard, complex problem and figure out, on its own, how to break it down.
Into smaller pieces.
Exactly. Into smaller, more manageable subtasks. Or even deciding, hey, this part is too hard for me. I should call a bigger, maybe more specialized model to help out.
Like delegate.
Precisely. Humans do this all the time, intuitively. We see a big project, we break it into steps. Language models just don't do this natively. It's a completely new capability we have to deliberately build into them through training.
If we want them to handle really tough multi-step tasks on their own.
Exactly.
Autonomously.
Okay, so we've got skills, calibration, strategy, and abstraction. These are the goals. How do we actually get these into the models? How do we train for this?
Well, the core training method that's being discussed, and the one that drove a lot of recent progress, is reinforcement learning with verifiable rewards, RLVR.
Okay, what does that involve?
It's basically a cycle. The language model generates some output, some completions, then it gets feedback on those completions, maybe a score, maybe based on whether it's verifiably correct or aligned with human preferences.
Right.
And then, based on that feedback, the model updates its internal weights. It learns what good looks like. The incredible performance jumps we saw in models like OpenAI's O1 and O3, a lot of that came from this newer training paradigm.
Teaching it to reason better. Exactly. And the argument is, we need to apply a similar, rigorous approach to develop these robust planning capabilities, too.
It really sounds like building these advanced planning abilities takes, well, a massive effort. What's the human role in all this? How significant is it?
It's fascinating, actually, the sheer human effort involved. Yeah. If you look at OpenAI's journey, say, with QStar, which kind of evolved into Strawberry and then the O1 model,
right.
That whole process represented something like 12 to 18 months of really intensive work. And not just building the model, but creating the initial reasoning traces, collecting a lot of human data.
Human data, why?
To make sure complex behaviors, like knowing when to backtrack if it made a mistake or how to verify its own steps, were actually reliable in the models. Humans had to provide examples of that good reasoning.
I see. That sounds painstaking.
It is. But for planning, here's the potentially good news. Generating good, say, 5 to 10 step plans for training data. That seems to be much more intuitive for humans than creating those super complex, detailed reasoning traces.
Ah, so maybe faster progress is possible for planning.
There's definitely some optimism there, yes. It might be an easier kind of data for humans to generate effectively.
Okay, this leads us to a really provocative thought from the source material. We usually talk about pre-training, building the huge base model, and then post-training, which is fine-tuning it.
Right.
What if we just started calling post-training training? Just drop the post. What's the thinking there?
It really challenges how we think about where resources go in AI development.
Yeah.
So for OpenAI's O1 model, that post-training phase, it was maybe only about 1% of the total compute compared to the massive pre-training compute.
Tiny, relatively speaking.
Very small. But then, with their next big model, O3, that post-training compute apparently increased tenfold. 10 times.
Whoa.
So, if that trend continues, we are getting very close, very quickly, to a point where the compute spent on post-training refining, reasoning, planning, calibration could actually match the compute spent on pre-training in terms of raw GPU hours.
Parity between pre-training and post-training compute.
Exactly. A concept that would have seemed, frankly, unfathomable just a year or so ago. It shows a fundamental shift in where the effort and innovation is happening.
That is a massive shift. Are there other signs, other examples pointing towards this growing investment in training beyond the initial pre-training?
Yeah, there are. Take the DeepSeek V3 paper. Initially, they reported a really tiny fraction, like 0.18% of compute spent on post-training.
Okay.
But then there was a deleted tweet, interesting in itself, from one of their reinforcement learning researchers. It suggested their main RL phase, their R1 training, took a few weeks, whereas pre-training took 2 months.
A few weeks versus 2 months.
Right. If you do the math, that implies the post-training could already be somewhere in the range of 10 to 20% of their total compute, much, much higher than the 0.18% reported.
A huge difference.
A huge difference. And it powerfully underscores this idea that scaling RLs, scaling reinforcement learning, is a very real thing. Labs are pouring more resources into it. It highlights why we really need models that can break down tasks and solve them autonomously, because that's where the heavy investment is increasingly going.
So this whole deep dive, it really shows that AI's evolution, especially in reasoning, isn't just about making models bigger. It's about smarter, much more intentional training.
Exactly.
Training them not just on facts, but on how to think, how to plan, tackling that overthinking with calibration, building in strategy and abstraction. It feels like the future hinges on designing how these systems learn to plan effectively.
And if you connect that to the bigger picture, it's clear that while models are gaining incredible skills, like that sophisticated search we talked about,
Right.
their true value, their reliability, will come when they can plan and execute tasks consistently. The difference between getting a masterpiece output, something genuinely useful, and getting a complete dud, often that boils down to this lack of inherent planning capability.
That gap between a cool demo and a dependable tool.
Precisely. Planning is the key to bridging that gap.
So here's a final thought then, something for you to chew on. If we can make these AI models truly native planners, really good at complex, multi-step problem solving, what kinds of tasks that seem impossible today might become just simple, reliable, everyday functions in only a few years? And maybe just as importantly, what new kinds of human efforts like generating that planning data will be needed to actually get us there?
That's the big question.
We hope this deep dive has given you a bit of a shortcut to being well informed on this frontier and maybe sparked some new curiosities. Thanks for joining us.